In previous video, we showed in the method of steepest descent algorithm, the update of the weight Wn plus 1 that's equal to Wn minus eta multiplied with Gn. And here, the Gn is the gradient of the cost function as we showed in previous video. That's equal to the product of y minus d multiplied with x transpose. And here eta is a new variable. We call that one is the step size or the learning rate. It is a positive constant. In the steepest descent method, the constant eta plays an important role. So the selection of eta is very tricky and need to be very careful. So if the eta is too small, as we showed in this case, the update from each training data is too small. Therefore, it will take a really long time to reach the optimal value at here. In another way, if we choose a big eta, the update weight will be bouncy back and forth, like we showed here. But it never can really reach the optimal value. So, in order to avoid too large eta or too small eta, we normally using a learning rate annealing method to find the optimal eta. So in this method, the learning rate starts from a relatively large value. And then the learning rate will gradually decrease with the increase of iteration. Stochastically, it can be approximate as eta n equal to c and over n. So here c is a positive parameter and n is the iteration. So this case shows how does this annealing approach works. So at the very beginning, we give a relatively large eta, so from here to here. And then with the increase of iteration, the eta becomes smaller and smaller. Therefore, it can make it reach its minimum value. Or we can define a more elaborate way to calculate the learning rate. That is eta n equal to eta 0 over 1 plus n over tau. So here, eta 0 and tau are positive parameters, and n is the iteration. So here, 1n is small compared to tau. The learning rate is approximate constant, like we showed before. It's an approximate constant. So 1n is large compared to tau. The learning rate follows the stochastic approximation as we showed in previous approach.